All right, guys, so let's move on to looking at an application of combinations. But to do that, we're going to actually start with something a little more basic. And it's something called the binomial theorem. So binomial means two terms, and we're going to be looking at when we have two terms in our base and we're raising it to powers that are integers. So for example, you can tell here I've expanded out x plus y. If I have it to the 0, that's easy, that's 1. X plus y to the first is just x plus y. That's easy. You guys are probably familiar with x plus y squared, right? We get this x squared plus 2xy. This might start to become new to the third power. Here we've got this guy expanded, and to the fourth power, we've got this guy expanded. Now, I think what's important to note, and so I'm going to write it over here again, is I really want you to pay attention also to the coefficients on these terms. So notice I'm putting ones in front of my squared terms just for the sake of you getting to see that value that's out there. So I want you to take a moment and I want you to look at, do you notice a pattern within this expansion? Any patterns? There's lots of patterns here, but do you notice any patterns in general? So take your time, take a look at them, look at how the terms expand out and see. This would be a good time to pause the video and take a look at how they expand. Okay, so some of the things that you might have noticed is that you start off with, like this is to the first, you start off with your x term or whatever your first term is to that highest power. So like this one is x to the first, this is x squared, x cubed, x to the fourth. And what happens is as you move through your terms in your expansion, your exponent on the x term goes down by 1, right? So like you start with x to the fourth, the next term has x to the third, x squared, and so on and so forth. So the x terms are going down in power, and at the same time, your second term in the binomial is going up. Like there are no x terms here, no y terms here, then there's a y to the first, y to the second. Technically, there is a y term here. You can think of it as 1x squared y to the 0, but y to the 0 is just 1. So that's why you don't see it. Okay. So that's one of the patterns, or those are a couple of the patterns that we see. Now there's also a pattern in the coefficients. Has anybody seen this pattern before? 1, 1, 1, 1, 2, 1. Maybe you noticed this already. Yeah, this is Pascal's triangle. And you get, if you add the two numbers above, you get that number below. So like 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, so on and so forth. That's how Pascal's triangle works. So interestingly, we see this Pascal's triangle in this binomial expansion. Okay, so this is obviously easy for us to then expand things that are two powers when there's a two-term base. Okay. Let's see. This is just me talking about those patterns. Okay, so let's look at an example. So here we go. We have x plus y to the 9th. So if I was trying to expand this guy out, and again, this one's pretty easy, then my first term would be 1, because that first one always has a 1. X to the 9th. Technically y to the 0, but we don't write that. My second term, we would have to figure out that second coefficient. It ends up being a 9. We can talk about that in a while. Or, I mean, we can talk about that later, how we get that. But then this power of x would go down by 1. This would go up by 1. And so on and so forth. And then we can keep getting this next coefficient. My next coefficient ends up being 36. Again, down by a power, up by a power, and so on and so forth. We're going to talk about a quicker way to get these numbers out front by looking at another pattern that we've seen. So let me go. I'm actually going to go forward a little bit to Pascal's triangle. So here's a big Pascal's triangle for you to see. So I want you to take a look at something. We've been doing a lot with combinations, right? So let's look at the 0 row. If I did 0 combined 0. So if I have 0 elements, then I take them 0 at a time. There's only one way to do that. So, and that's it. There's no other options because you don't have any elements. If I have 1 element, then I have 1 element and I can either take 0 or I can take 1. Like those are my options. And guess what I get when I look at those two? 1, there's one way to take nobody, and there's one way to take both, one way to take the 1 element. So I get 1, 1. How about for 2? Well, if you have 2 elements, you can either take nobody, you could take 1, or you could take 2. And guess what you get? 1, 2, 1. So what are you noticing? If you look at the different combinations, you get these values on Pascal's triangle. So again, let me just pick one. Like if I picked the 4th row and I did 4C0, 4C1, 4C2, 4C3, 4C4, which are all the different combinations of choosing 0 elements all the way up through 4. I get 1, 4, 6, 4, 1, which are the coefficients here, which remember, let's go back, are the coefficients in front of your expansion. This is huge. So this gives us a huge pattern for expanding a binomial. So for example, and the way that we write that is we use this notation. So like you guys are comfortable with NCR. This is called classical notation, and it's like you have this 2x1 matrix, but it's a parentheses. This is classical notation, and it just means to do the combination. Oops. So for example, if I wanted to find the first term, we would already know that it's an x to the 9th, y to the 0. Again, we don't write the y to the 0. And you guys know that it's a 1, but if it's the first one, you would do, I have 9, do it to the 9th power, so 9 objects. And the first one is always 0 because you're doing it taking none. And that comes out to a 1. If I was doing the second term, I would do 9C1. And then obviously down by a power, up by a power. Guess what 9C1 is? 9. If I wanted the next term, I would do 9C2, and then down by a power, up by a power. And that's how I got 36, and so on and so forth. Okay, I think something that's important to note here is that the first term isn't blank C1 because you always start at 0. So make sure that you focus on that you realize that. Another easy way, another pattern you might see is that this and the power on your second part of your binomial always match. So like if I'm trying to find the first term, that's technically when this is to the 0, which is also 0 here. Or like if I'm finding my second term, that's actually 1 power on the y and 1 here. So like that's an easy way to match them up. And we'll do some examples in a little bit, and you'll get to see that in action a little bit more. Okay. All right. I think now is a good time to let's just try some and see. Oops. Let's try some and see how you guys do with that. And then I think you'll see some of these patterns kind of start to emerge. Let me get a little bit better. There we go. Okay. So let's try some of these together and see how it goes. And I'm not going to make them super easy because, well, that's no fun. So let's do, I'll bump it up a little bit. I'll do 2x minus, plus 3y, and we'll just do to the 4th. Okay, so we're going to expand this one all the way out. So we're going to do every single term. In the future, I may only want one specific term or so, but we'll start here. Okay, so first term, well, remembered, to get the first term, you have this combination coefficient, which it's 1, but I'm just going to show you that it would be 4C0, which, yes, in fact, is a 1. Okay, then it would be your first term, careful, which is 2x all the way to the 4th. And then technically 3y to the 0, but we don't need to put that because we know anything to the 0 is 1. Okay, plus my second term would have this 4c1. Then it would be 2x down by a power. Second term, up by a power. Then 4c2, 2x, 2x down by a power squared, up by a power squared. 4c3 down by a power. down by a power, up by a power. And last but not least, 4c4. This is gone now completely, and you should just have your 3y to the full power of 4. Okay, so again, if you already know your expansion for the fourth row, then that makes this a lot easier. We can also do it in our calculator, and we can do it quickly. So let me show you how we do that, how we kind of attack that in our calculator, because we can do multiple combinations at once. So let me show you how to do that. So in my calculator, when I go to do combinations, I have to put the first number first. So I'm going to go ahead and put the 4. I'm going to go to math. I'm going to go over to probability and choose combination. Now check this out. You could do each one individually, or you can use set notation like we've done before and list all the ones that you want with commas in between. So I want 0, 1, 2, 3, oops, all the way up through 4. And then don't forget to close off your set, otherwise it won't work. So when I hit enter, this will give me all of those in one set. So I know that my coefficients are 1, 4, 6, 4, 1, which is that fourth rule or fourth row on Pascal's triangle. That's just quicker, so that you have all those. All right. Oops, does not want to come back. There we go. So this is 1, this is 4, this is 6, this is 4, that's 1. All right, now let's fill in what we've got. Make sure the biggest mistake people make here is they don't do the power for both pieces. So like this is going to be 2 to the 4th. So 16x to the 4th. Then you've got that 4. Then we've got 8x cubed times 3y. Then we've got the 6 from here, 4x squared, 9y squared, 2x, 27. Careful, make sure you're doing powers, not multiplying. And then 1 times 3 to the 4th is 81, y to the 4th. And then you just have to simplify. So like my final answer here comes out to, let's see what we get, 16x to the 4th. I have to do some of this math because I did not. I just made this one up. Okay, so 24 times 4, 96 x cubed y plus 324 x squared y squared, 216 xy cubed, and then 81 y to the 4th. So there's that expanded version. Okay, so let's add some dimension to this. Let's try what happens if I take something to like a negative power, or I'm sorry, what if I have a negative and maybe some powers inside? So let's do, I'll change it up and use different variables too. So let's do a squared minus 3b, and I'll take it to the 3rd. I'm trying to keep the powers low for now because we're doing a full expansion. Okay, so first of all, I would get my coefficients for 3 for the 3rd row, and so those are 1, 3, 3, 1. Then so then you already know what your expansion is going to look like. I'll still do the classical notation to show you guys that, but okay. If you have minus, guys, all you need to do is think of this as plus a negative. So just think of this second term as being negative, which is important when you come to expanding it. Okay, so I'd have 3c0. I'd have the first term to the full power, and the second term would be to the 0, so I don't have to worry about it. 3, 1. If you want to pause this and try it on your own and come back, you can. And then I have a squared down by a power. This term, careful, negative 3b up by a power. 3, 2. A squared down by a power to the first, negative 3b up by a power squared, and then 3, 3. Oops, there is no a squared, and negative 3b to the 3rd. Okay, so what do we got to watch out for? Obviously, that's a 1. This is always a 1, and so is that. So some people just get to the point where they kind of leave this off because they know it's going to be a 1, and that's fine. So this becomes power to a power is multiplication, a to the 6th. This is 3a to the 4th times, careful, negative 3b. This guy is 3, a squared. Negative 3 squared is 9, b squared. Take your time on these. And then last but not least, we have negative 3 to the 3rd, which is negative 27b cubed. And then just simplifying. So a to the 6th minus 9, a to the 4th b. plus 27a squared b squared, and then minus 27b cubed. So this one looked a little weird because of the fact that there was a power on the inside. So like your highest power on a wasn't to the third because it was already squared. So that's why you saw it go from a to the sixth, a to the fourth, a squared, no a, right? The b was just to the first, so that went up like normal. Okay. So in general, that's how we do these. That's how we expand these out. But sometimes we don't want the full expansion. We just want a particular term in the expansion. So let's look at what that would be like. So let's say, so I'm going to make the powers much higher because we only want like a specific term. Okay, so let's do 3m minus 2p to the 8th. And let's say I want just the coefficient on the m to the 5th, p to the 3rd term. So I want this part. I want what ends up being in front of it. Like if I go back real quick, I'm talking about like I want the 27, I want the -9, I want what's in front of that at the end. Okay, so we have to figure out where this fits in. So the first thing that I would do is start by actually looking at what makes up this term, right? So I'm going to get rid of that for a moment. So if I have m to the 5th, I know that I must have raised this position to the 5th power. Okay. I've got a negative 2p for my other position. And I know that, again, that one would have had to have been raised to the 3rd power because otherwise I wouldn't come out with that. Okay, so I've got those two pieces. Now I just have to figure out what the combination was that's out front. I know there's 8 terms. I know it's 8. Question is what goes here. If you remember me talking earlier, the power on the second term always matches. So there we go. Then we just have to figure everything out. So then you could get out your calculator and you could do 8 C3. So I'm going to figure that guy out. So that part's 56. Careful. I have to take 3 to the 5th as well as m to the 5th. So this part is 243 m to the 5th. I have to take negative 2 to the 3rd, which is, careful, negative 8 p cubed. So the coefficient is going to be made up of this, this, and this. All those parts play a crucial role. So make sure that you have all of those pieces. So my coefficient ended up being negative 108,864. Okay, let me give you one to try that you can pause and then look at the answer. So here's another one. So how about, I'm going to mix it up a little bit. So let's find the coefficient on, this one's a little different, so we'll see how you do with it. The x to the 3rd, y to the 14th term. Okay, so you can go ahead and pause this and take a moment to solve. Okay, so hopefully you took a moment to solve. So let's look at what's happening. If this is to the 3rd, then that means I would have taken this first position to the 3rd. And the second position, which is y squared, normally you might say, well, that's to the 7th. Or I'm sorry, you would say that's to the 14th, but it's not. Remember, these two things right here, these exponents should always add up to 10. I don't know if you guys noticed that as another pattern. Like, let me just clip back here. Like your exponents always add up to, that's a 1, your power, right? Because as this one goes down, the other one's coming up. So like according to that, this should be to the 7th, which is true because then squared to the 7th would result in a 14th. So just don't automatically put the 14th there. That wouldn't make sense. Okay, and then I need my coefficient. So my coefficient is 10 objects. C should match 7. So again, making sure that you're not putting a 14. All right, so let's do this thing. So 10C7, oops, gives me 120. For this guy, I have to cube both parts. 27, 4 cubed, 64, x cubed. It's just a fraction. Don't let it freak you out. Y to the 14th. So then I'm going to have to multiply these two pieces together to get my coefficient. So I've got 120 times 27 over 64. I'm going to leave it as a fraction. So I got reduced 405 over 8. Now, technically, that's also 50.625 perfectly. It comes out perfect. But again, a fraction is just fine. Okay. Okay, so not too bad. Let me flip it a little bit. Instead of asking you for the coefficient, I'm going to ask you for a particular term. Okay. So let's say we want to find the 9th term in the expansion. Let's do 5a minus b squared over 4 to the 15th. Whoa. So first of all, we want the 9th term. And this is really, this goes back to that, the initial ones where we expanded them out. So let me go to some of the ones where we did like the full expansion. This is important to remember. Your first term was not blank C1 and to the 1. Remember, it was blank C0. My second term, for example, my coefficient was blank C1. So it's important to remember that if I say like I want a specific term in the expansion, then you need to go one less for your combination, right? Because remember that first one is a 0. So, okay, knowing that, if I want the 9th term, the first thing I know is that I would be 15C8 out front, because remember we start with a 0 for our first term, so it's always one less. Once you get that, it's a little easier to figure out what these powers should be. Why? Well, this should match here. And these two things have to add up to what? 15. So that's to the 7th. Then just fill in. This would be 5a, negative b squared over 4. And then let's go to work. So I have 15. These numbers do get big pretty quickly, but I have 6,435 here for my combination. Here I have to do 5 to the 7th. That's going to get pretty big. 78,125, a to the 7th. This one is going to be b to the 16th, and because it's a negative to an even power, it'll be positive. And then let's see, we have 4 to the 8th on the bottom. And that gives me 65,536. Okay. So let's finish it out. I know it's going to be a to the 7th, b to the 16th, and then I'm going to multiply these two and divide by that. So let's see, that's going to take me just a moment to plug in. And I will leave it as a fraction in reduced form. Oh, it doesn't come out very nice. So I'm not sure if the fraction was so nasty, but let me try it one more time. I'll do it as an actual fraction in the calculator. I think the numbers just get so large that it doesn't necessarily maybe reduce to anything nice. It doesn't. So, so in this one, I guess you'd have to almost leave it as this. Let's see. Whew, it's a very big number. I don't usually give numbers quite this big, so that's my fault for making one that's so large. So the problem with this, again, guys, is that when I actually do it, it doesn't reduce. It comes out, I mean, it's such a nasty decimal, so that's why I just left it as a fraction. I don't usually give ones that are quite this terrible, just so you know. Okay, so I'll give you one more and you can try it. You can pause it and try it on your own. Okay, so I'll try to keep the numbers down. So let's do, let's put a negative here. Ooh. Negative 2x to the 3rd, and let's do plus 1/3 y. Just do 1/3 y, and we'll say to the 8th. Okay, so let's say we want to find the 6th term. So again, go ahead and pause it. Notice I'm not saying the coefficient, so I'm with the full 6th term. Okay. Hopefully you've given this a shot. So if I want the sixth term, that would be 8C5. Remember, you start with a 0, so it's always one less, which means this guy is to the fifth. This guy, add up to 8, is to the third. Fill in your two pieces, and then start your work. So I have to do 8C5, 56. I'm going to do negative 2 to the third, which is negative 8, x to the multiply, 9th. Here I have y to the 5th over technically 3 to the 5th, so I'm going to leave it like that, 243 down here. And then I'm just going to multiply everybody together. So let's see what we get. 56 and negative 8. Oops. And then divide by the 243. Let's see if this guy reduces at all. It doesn't. So we would leave it negative 448 over 243. That's the best we can do there. Okay. So then I can get a little bit nastier by giving you like things that have fractional exponents inside. I can give you negative powers on the inside. And so I can make these questions a little bit more challenging. So I could do like, you know, x to the negative third plus 5y squared, you know, again, to the 11th. And I could ask you for the fifth term. Ooh, actually, you know what? I like this better. Let's do this. Let's make them both x. There we go. Let's do the fifth term. So let's see what happens when they're both x's, but because they're different powers, you know, you couldn't combine like terms beforehand. So if I wanted the fifth term, I would start out with 11c4. Second would be to the fourth. Add up to 11 would be to the seventh. I'd put my x to the negative 3 here and my 5x squared here. Okay, 11c4 is 330. This is, I would probably actually think of this as 1 over x to the 21, right? Because it's technically x to the negative 21, but if I look at it this way, I can, you know, keep it positive. Here, I would have to do 5 to the 4th, so 625, and then I have x to the 8th. So I could reduce this. Let's see, I'm going to have to take the 625 times the 330, but so let me start with that. That's out front, but then I have an x to the 8th over an x to the 21. Yes, you should reduce that, right? Remember, that's just subtraction. So I have 206,250 over, and then we're just taking 21 away from 8, x to the 13, or suppose you could say 206,250 x to the negative 13th, but I prefer positive exponents, so I would do it like that. Okay. So that's the binomial expansion, guys, and it allows us, again, to take something that is a binomial and expand it out as far as its powers go. You're going to get some practice with some very interesting ones from the problem set, but in general, this should be probably one of the easier things that you do for this chapter. I think the combinations and permutations can get a little bit tricky in some of those more aggressive problems. So enjoy this and have a wonderful weekend.